No, at the end.
At the end, right? Okay. So welcome everyone to this this seminar. First, before I start, the plan is to record, and in fact, I think we're recording as we speak. So if anybody objects to this, then you know, do let us know. But if everybody's happy with it, then I guess we'll just continue. The plan is also to have an interactive exchange. We have quite a bit of time this afternoon or this morning, depending where you are. So feel free to ask questions. Probably the easiest way is to, when Avi will be speaking, to put a question in the chat, and I'll be monitoring the chat, and then you know, we'll try to manage as best as I can. So without further ado, let me introduce our speaker. It's a great pleasure to have Avi Wigderson. Did I pronounce this right, Avi?
Wigderson.
Wigderson. Give a talk this morning, this afternoon, today. So Avi is we always say the speakers don't need any introduction. This is probably even more true with the speaker we have today, but I will nevertheless say a few things. Avi is a theoretical computer scientist and a mathematician who has worked in many areas, in particular complexity theory, but he has contributed to results, seminal results in several other areas, including cryptography, distributed computing, neural networks, and so on. He was born and he grew up in Israel, and he studied at I believe, at the Technion in Israel, and then did his PhD at Princeton, working with Richard de Clipton. And he was then at Berkeley and at the IBM Almaden Research Center in California, and then at MSRI in Berkeley, then at Hebrew University, and then for the last 20 years or so, he's been at the Institute for Advanced Study in Princeton, where he's speaking to us from today. He has won many awards. He most recently won the Abel Prize, which is spectacular achievement in its own right, but also because this was joint with Laszlo Lovash, because it is the first time, I believe, that somebody who's at least partly identified as a computer scientist wins this award. I mean, it has in the past been given exclusively to people who were sort of describing themselves solely as mathematicians. In fact, many of the previous winners have won awards such as the Fields Medal. The Abel Prize, of course, is considered to be, alongside with the Fields Medal, the top prize in mathematics. Avi could not win the Fields Medal because he won the Nevan-Lina Prize, and it is specification that if you win the Nevan-Lina Prize, you cannot be awarded the Fields Medal. So perhaps that explains why you know, he's a Nobel Prize winner that does not have a Fields Medal. He's also won the Gödel Prize and the Knuth Prize, and it is a real pleasure to have him speak to us today on optimization and complexity theory. So,
yeah, thanks. Okay, let me see that I can. It works before. How do I share the screen now?
Looks perfect.
Okay. Okay, I hope everybody can see this. Yeah, thanks for the invitation, and I'm really happy to be in this forum. I took a look at the list of names and faces, and I don't know most of you. I also don't know, you know, the backgrounds of people in the audience. This story I'm going to tell you, it's really, I think of it as a story because it's you know, summarizing work I've been doing, something new for me in the past 5 or 6 years, very different than things I've done before, even though the motivations for it came from things I'm very interested in, and I'll explain this. For me, it was a learning experience because, you know, many new areas that I was not familiar with, I had to, you know, I had to learn, and was really surprised and happy to discover ways in which they connect. So I think that you know, there's no one person expert in everything, but all these areas I'm talking about, I'm certainly not. But I want to tell you, you know, the story of this work, how it evolved, and what we know today, and lots of things we still don't know, and hope to find out, maybe with your help. So it's the title is Optimization, Complexity, and Math. That's complexity is where I come from. These problems that we'll discuss have a lot to do with optimization, and as I mentioned, connect to various areas of mathematics. And the subtitle I'll get to. I mean, what does it have to do with the P versus NP and gradient descent? You'll see as we go along. This set of works I'll be talking about. You know, I have many co-authors. There are probably now about 10 papers, dozen papers on this subject, so they are listed below. Okay, let me start. Before I start, I want to do my usual, you know, commercial. I wrote this book a couple of years ago. It's, I mean, if you like the design of the cover, you can buy it, but you don't have to. It's available freely online. It's an invitation to computational complexity. And it's written for people who are not, I mean, also for experts, but also for people who want to get into this area and learn about it. So you'll find there are lots of things that I'm not talking about in this lecture. Okay, let me start. So again, you can stop me with questions by chat, or if you know, it seems like a pressing question that others might not understand, just interrupt me. The plan is to start from describing one single problem. I'll explain it, singularity of symbolic matrices, and one algorithm for it, which is alternating minimization, which I'll explain as well. And then analyze what we are doing, and then try to generalize it. And we generalize both the problems, the algorithms, the tools we use, and it repeats itself, this cycle, several times. That's at least how I view the evolution in the past few years. And at the end, you know, we got to an understanding of something quite general, extending the standard convex optimization framework in Euclidean spaces to basically Riemannian manifolds, to non-commutative settings where convexity is replaced by geodesic convexity. Again, I will explain you know, what this means when we get to it. But yeah, I find it a very nice sort of place to stand, and still, as I mentioned, lots of questions unanswered. The areas that are touched by this work, as I mentioned, are many. There is a list here that I can read, and there were, you know, so non-commutative algebra, invariant theory, which is really central, quantum information theory, analysis, operator theory, statistics, and for me, computational complexity. It's the origins of my interest in that, and optimization in some of the consequences these algorithms provide. I'll explain some of these in more detail as the talk continues. I just want somehow to impress on you how you know, nice this. You know, I said I'll discuss one problem, and then it connects to all these areas. So many of these areas are connected. Some connections were known, some are new because of this work, and I'll explain some of this. And again, because you know, it involves so many areas, when I was invited to give this talk, I was told that people would like to see proofs. I will give you some proofs or ideas of proofs, but I think it's more important just to understand the notions, the problems, and the connections in this work. But anyway, you can ask me for more details as we go on any topic. So as I mentioned, we want to study one algorithm for one problem, and I want to describe this problem first, and then the algorithm. And actually, to describe the real problem, I'll describe a baby version and then continue to the real one. And the baby version I mentioned because it's familiar to everybody. It's a perfect matching problem. You are given some bipartite graph, and you want to know whether you can match the left side to the right side. So, you know, if my kids, you know, each prefer some, you know, willing to have some candies and don't want others, and this is depicted by these edges in the graph. What we are looking for is a way to give each child a candy so that which they like. So this graph G prime here has a perfect matching, and this is a graph which does not have a perfect matching, and you can easily see that. So the general computational question is when, you know, does a given graph whether a given graph has a perfect matching. This has a very efficient algorithm, a polynomial time algorithm. It turns out that even though, you know, we think of it as being discovered in the 20th century, it's more or less the famous, you know, augmenting path algorithm exists already in the work of Jacobi in ordinary differential equations, systems of ordinary differential equations, you know, in the 19th century. Anyway, it's a simple problem by any standard, but I want to talk about different representations of this problem, and in particular algebraic representation. So what's a natural way to ask this question algebraically? You can look at the adjacency matrix of the graph. So it just writes the vertices, the sets of vertices U and B in the rows and columns, and put a 1 if there is an edge between them, between a pair of vertices, and otherwise a 0. That's the standard representation of a bipartite graph. And now a perfect matching exists if and only if the permanent of this matrix is positive. What's the permanent of a matrix? It's just like a determinant. It's you know, without the signs. It counts, you know, it just goes over all diagonals in this, general diagonals in this matrix, and multiplies the entries. So, you know, generalized diagonal, picking, you know, one from every row and one from every column is really a matching. So you are just summing up over all potential matchings and check that all edges exist. So that's a simple observation. And it's an algebraic way to capture perfect matching. And the point is that permanent is a complicated function to compute. It's a different story for a different talk. But the question is whether there's other algebraic expressions, and one beautiful one was provided by Edmonds. So here's Edmonds' idea. You know, you can, instead of putting ones to represent an edge between I and j, put a variable xij if there is an edge. And otherwise, if there's no edge, keep it as 0. Now the matrix becomes a symbolic matrix, a matrix with variables. And his observation is the following, is that the graph has a perfect matching if and only if the determinant of the symbolic matrix, which is now a polynomial in the variables, is not identically 0. So again, it's equivalent to perfect matching, so it has a polynomial time algorithm, this question. I just want to you know, explain why it's true. It's very simple. Determinant has signs, so potentially things can cancel. But because we put different variables in the different boxes, you know, any monomial, if there was a perfect matching, any monomial will have variables that don't exist in other monomials, so there can be no cancellation. This is a very simple observation. Okay, so that's this case of perfect matching. Now, here's a sort of an amazing leap that Edmonds made, and he asked the following question. So this problem, this particular problem with distinct variables is, you know, efficiently solvable. How about putting not just single variables at every coordinate of this matrix, but just allowing an arbitrary linear form. Okay, so you have now as your input a given matrix. Every entry is a linear form in some set of variables. And we wonder whether so one way to represent it is just the coefficient matrix of every variable, right? So we are given a list of matrices in whatever field we are. We'll be mostly concerned with the rationals, but this is interesting over any field. So for every variable has a matrix coefficient, and the linear combination of these matrices, sometimes called the linear pencil in mathematics, is the input to our problem. And what do we want to know? We want to know the same thing we wanted before. Is the determinant, which again is a polynomial because it's a determinant of these entries which are linear form in variables, is the determinant identically zero. Okay. We knew how to do it in the special case of single variables, but what about general linear forms? So it's a problem. You can care about it or not. We'll see why it's interesting. Okay, so I hope this problem is clear. Again, please ask if or stop me if not. This is a basic problem. This will be the basic problem we'll be interested in, well, a variant of it. Yeah, so let me continue. If you think my pace is too slow, too fast, just tell me. Okay. That's a problem we'll be interested in. And what do we know? So Edmonds, as I mentioned, asked the question whether it has a polynomial time algorithm. Lovaas observed, that it has a fast probabilistic polynomial time algorithm. This is really simple. I mean, the idea is just you plug random values to the variables, and you compute the numeric determinant. This is something that can be done efficiently. And the reason it works is that, of course, if the polynomial, the determinant was identically zero, then whatever you plug in, you get a zero. Otherwise, it's, the zeros of this polynomial have measured zero in space, so the chance you hit them is very small in a random point. So that's a very simple idea that's been used a lot. And that was, now I want to explain why, why the interest besides curiosity in this problem. There are two or more reasons. The first came with Valiant, actually at the same time, but in a different world. Valiant, in his algebraic complexity theory, proved that the determinant of matrices like this, of symbolic matrices, actually represent any algebraic identity, any identity with polynomials that appear anywhere in mathematics. Let me be vague enough for that. Can be reduced to the question of whether the determinant of a symbolic matrix is identically zero. So to this singularity problem. Okay, so it captures all of the algebraic identities, and certainly people in algebra in general in math would like to prove identities. So one can think they would like to prove these identities. How do you verify an identity? This captures many problems in the various areas of mathematics, and maybe for the same reason it comes up a lot. But the reason it's really important to solve this problem, in particular, solve the problem in deterministic polynomial time as opposed to probabilistic polynomial time. So Edmonds' open problem was discovered about 20 years ago, and it's this result. It's due to Cabanes and Impagliazzo, and it says the following. If you can find a deterministic polynomial time algorithm for a singularity problem, then you essentially proved something like P different than NP. I'm not going to go in here to the, what is the meaning of the quotes. I mean, you would have proved a major result in complexity theory that's very similar to the P different than NP conjecture. And so it will be an absolutely major development if you manage to have a polynomial time algorithm for things. What I want to stress is that, I mean, if you've never seen this before, this result, it's really amazing. The left-hand side says that we can solve one problem, one particular problem efficiently. And it implies the right-hand side, which says that, other problems, like NP-complete problems, are hard. So the ability to do something fast implies that other problems cannot be solved quickly. It's really beautiful, and in fact, it's not so difficult with the standard tools at the time of complexity theory, but it's a fundamental result, and it's of course great motivation to try to solve this problem. We have a path to proving P different than NP just by developing an algorithm. This problem, we have a probabilistic algorithm and we like to remove the randomness from it. So that's a de-randomization type of question. And it also implies hardness, lower bound. So these are the motivations for me to work on this problem. And we'll see how, well, we may discuss how these issues come up, but we'll focus now mainly on the algorithmic task of finding such an algorithm. I can tell you already, we are not going to solve it. I mean, you would have heard if we proved P was different than NP. So we don't know the answer to this. This remains an open problem, maybe the most important open problem of this talk. And what we are going to do is what mathematicians always do when they can solve a problem, they change the problem. So let me explain this. So here's the problem again. I want to tell you about the dual life of symbolic determinants or symbolic singularity. We fix a field F. We are given a bunch of matrices which define this linear pencil, the symbolic matrix L of X. And we ask whether this matrix is singular. So until now, I didn't say anything, and everybody assumed, like I expected you to, that we are talking about variables which commute. In this case, of course, this is the same as asking whether the determinant is identically zero. But you can ask about singularity, and singularity of the symbolic matrix happens in the field of rational functions in this variable. So that's the question. And what we know, I said already what we know it has a fast probabilistic algorithm, and it's a great problem to do it in polynomial time. We don't know how to do this. So let's look at another natural case, is when the variables do not commute. It's as valid a question. This is a non-commutative singularity problem. And if you try to understand what it means to, whether a matrix is singular in over non-commutative variables, I tell you already, this is a very complicated thing to even define. It turns out that there is an analogous field, maybe some of you are familiar with it, analogous field to the field of rational functions when the variables do not commute. It's far, far more complex objects. Elements there are not ratios of polynomials at all. But anyway, there's a mathematical way to define this question. We will see elementary ways to define this question, so we don't have to go into the definition of the free square field. But what it seems is that this is a much harder problem. It took quite a bit to even prove that this problem, this non-commutative version of singularity of symbolic matrices, is decidable. It's not obvious that it's decidable. And Kohn proved it decidable, and the best algorithm that was known before this work I'll describe was exponential time. There was no, whether you allow randomization or not, there was no algorithm that beats exponential time. And so the main thing I want to tell you, this is a problem we'll focus on for now, this non-commutative singularity. I want to tell you to arrive at a deterministic efficient algorithm for this problem over non-commutative variables. This for the field of rationals or any field of characteristic zero, really. And soon after came a very different algorithm. So the first is with Garg, Gurwitz, and Oliveira. And soon after, Ivanios, Kjau, and Subramaniam found a very different algorithm to do it, in fact, over any field, essentially every field. These algorithms are different in nature. Ours is analytic, and that will be the focus of this talk, and their algorithm is algebraic, and I will not discuss it here. Okay, so we are looking for an algorithm for this strange problem. Again, I did not motivate this problem. I motivated the commutative version. I did not motivate this one. It turns out to be, at least as I don't know, extremely interesting, mainly because of the connections to many areas of math and the type of problems that are indirectly solved by it. So we'll see a list later. Okay, so now we describe the two problems we are interested in, and this non-commutative singularity and its baby version, the perfect matching. Now I want to talk about the algorithms to solve these problems. And again, I'll start from an algorithm for the baby version, but an algorithm that probably most of you have not seen, and then extend it to solving the non-commutative singularity problem. Let me ask again, anybody wants to ask a question or...
So Avi, we have a couple questions, in fact, in the chat. So one question is that, is it true that if polynomial identity testing is in polynomial time, then SING is in polynomial time? And I assume this is the case, right?
Yes, yes. So yeah. The valiant result that determinant is complete, symbolic determinant is complete, is really the statement that polynomial identity testing can be reduced to determinant testing, to this, yeah. So right. It's that's right. So I don't know how many people know the polynomial identity testing, but it's just basically I give you an algebraic circuit and ask whether the polynomial computes is identically zero. This can be encoded as a question about determinants of linear forms. Yes.
And the second question is whether SING is in co-NP.
No, in fact, I mean, no, in the sense we don't know. The Cabanetzin-Pagliazzo result holds in the same way if you replace P by co-NP. So if you have certificates of polynomial being identically zero, short certificates, that will also have the same implications. So yeah, it's a very good point. Thanks.
Thanks.
Okay. Okay, good. So you remember the perfect matching problem, and we know it as a polynomial time algorithm. Undergrads learn it in algorithms course, famous augmenting path algorithm. I want to talk about the different algorithm for the same problem. So let me first give you another version of perfect matching. It looks like a different problem. This is a matrix scaling problem. So what's the matrix scaling problem? It's very old. It starts probably in the 30s in the previous century, but Synchron is mainly identified with it. You get as input a non-negative matrix. Okay, matrix maybe with real numbers or rational numbers, non-negative A. First, a definition, matrix is called doubly stochastic if the row sums and column sums are 1. Okay, and the question is, if I give you a matrix and it's not doubly stochastic, can you make it doubly stochastic? And make it, what are you allowed to do? You're allowed to scale. And what is scaling? Scaling is multiplying rows and columns by scalars. So in other words, you are allowed to pre and post multiply your matrix by diagonal matrices, and you hope that the result is doubly stochastic. So make it more precise, a doubly stochastic scaling problem. You need to find or just decide if there exists such diagonal matrices so that the product has row sums and column sums approximately equals 1. So I want to stress this. It may not be the most natural question. This is the natural question, rather than equal. And by approximately equal, I mean that for anything close to 1, you have such scaling factor. So you can approach doubly stochastic as precisely as you wish using scaling. The reason that this is the right question to ask is that in this formulation, a matrix has this property, it's scalable, if and only if its permanent is positive. Okay, so if it was a 0 and 1 matrix, it would be exactly whether it has a perfect matching or not. So it's another formulation of our question. And the reason it was studied, it's a very interesting problem, very important problem. It came up in numerical analysis. There's application signal processing. We used it. I mentioned this in algorithms for approximating the permanent function, and so on. So anyway, this will be the problem we want to solve because it's equivalent to matrix scaling. Okay. So let's see what Sinkhorn and others, in fact, suggested to solve this problem. So think about it. You want to make this matrix, let's say the adjacency matrix of this graph, doubly stochastic. You want the row sums to be 1 and column sums to be 1. And it seems like, it's not obvious what to do because the constraints, of course, conflict. From one point of view, you can see it's a fair game. It's there are roughly 2n degrees, constraints, the row sums and column sums, and there are roughly 2n, degrees of freedom. You can find this. It takes the scaling coefficients. There are 2n of them. So of course, not every matrix is scalable. Like the all 0 matrix is non-negative and cannot be scaled. So yeah, it's a non-trivial question. It's equivalent to positivity of permanence. So let's see what we can do. And staring at it, there's one obvious thing we can do. We can solve half the problem, right? We can, for example, really trivially make all the row sums 1, right? So it's just if you divide every row by its sum, you get it, the row sums to be 1. So you can solve half the problem. And the amazing, you can think of it as bold or naive or, a beautiful idea is to just deal with these parts separately. So you scale the rows, right, in the obvious way. And now you look at the columns, they are not scaled. Right? So you say, okay, let's fix the columns. Okay, we fix the columns. That's also easy to do. And you look at the rows, you screw them up. Now they are not, it's not row stochastic. So you can, fix the rows again. And this is the idea. Let's just iterate this. This is what's called alternate minimization or alternate. Just try this and hope for the best. So let's see what happens here. You may notice that how the behavior is. I mean, if you look at the limit, this is what you get. You'll just cycle through this thing. It doesn't stabilize. It doesn't stabilize. There's no convergence here. And maybe it's good because this particular graph I use doesn't have a perfect match. Anyway, that's one observation. So we tried this algorithm on this graph. Here it didn't converge and it doesn't have a perfect matching. Maybe I should state the algorithm more precisely, even though I think it's obvious. You just are given the matrix, and if we let R of A and C of A be the inverses of row sums and column sums, then you basically alternate, multiplying by it either on the left or on the right to do the right thing. And you repeat it, we'll see that a few times, polynomial number of times will suffice. But that's the algorithm. So let's see. I think it's good. Yeah, I mean, of course, if any row sum is or column sum is 0, then it means that all entries are 0, and then there is no. You can answer immediately no. Okay, so I think we need another example to see how this works. So let's look at this example. This is the other graph we had in the beginning. You can see that this does have a perfect matching, the anti-diagonal corresponding to this graph. Okay, so let's run this algorithm. Scaling the rows give us this one. Scaling the columns do this. well, you probably will believe me, you don't have to calculate it. But if you look at this pattern here, you see that the numbers of the anti-diagonal are shrinking and those on the diagonal are increasing. And in fact, the limit here is, that particular perfect matching. So it does converge. And as I said, this has a perfect matching. The permanence is positive. So maybe it's also good. And in fact, it is. And there's a general theorem. Let me finish a complete statement of the algorithm. So you run through these iterations only a polynomial number of times, like n cubed times. And when you are done, let's say you scale the rows, so just look at the columns and see how close this vector is to the all ones vector. So how close the matrix is to doubly stochastic. You can do it in any norm you like. I mean, it's at this level, it doesn't matter, say in L1. You test whether the columns are close to being scaled. And, yes, you say the permanence is positive. No, you say the permanence is 0. So that's a very simple algorithm. And the main point is that it works. So it gives the right answer every time in a short amount of iterations. There are many analyses of this algorithm. I want to tell you about an analysis that Lineal Samornitsky and I came up with about 20 years ago in the context of approximating permanence, because this type of analysis will persist throughout the talk.
Avi, can I interrupt
yes.
a couple questions?
Yes.
So somebody's asking, what if there are multiple perfect matchings? Does the alternating minimization converge to one of them in particular?
Yeah, it's an excellent question, and I wish I knew the meaning of the limiting matrix. Here's some obvious facts I can tell you. If an entry, let's say positive entry, does not participate in any perfect matching, then it will be sent to 0 by this algorithm. If an edge participates in every perfect matching, it will be sent to 1. And otherwise, there'll be some, positive numbers there between 0 and 1, whose meaning I don't know. And I find very interesting. And I thought about it, and it's really interesting. But every perfect matching will survive, right?
Thanks. Just a quick question, which was asked a while back, but perhaps we can ask now. Is there a relationship between the non-commutative version of Zing and identity testing of polynomials given by non-commutative circuits?
Yes, so I'll talk about this a little later, but the answer is yes. It's related to even a more complex problem, which is rational identity testing, namely testing rational expressions. In polynomial identity testing, you look at circuits which do not allow division, and for polynomials, it doesn't matter whether you have divisions or not in the commutative case. In the non-commutative case, as I said, that's a very complex beast, and it's this question, non-commutative singularity, captures the word problem over this free skew fields. Namely, I'll give you a rational expression, and just an expression with plus, times, divide, and field elements in non-commutative variables, and I ask you whether this expression is identically 0. This is captured by the result of Kohn by this non-commutative singularity. So the answer is yes. So it solves this problem. Yes, absolutely.
Thanks.
Yeah. Okay. So so we have the algorithm, and now I want to explain the analysis of the algorithm, right? Because it's simple. That's the main message. It's really simple the way we did it here. It's also enlightening for the subsequent things we'll do. So how do you analyze such a it's basically a dynamical system, right? It's an evolution of matrices under these operations. And you want to prove convergence in any dynamical system, you find some good progress measure. and you want some basic properties of this progress measure. And it turns out that it's really nice to pick the permanent of the matrix itself as the progress measure. Of course, if it was 0 in the beginning, it will stay 0. So it's interesting to see what happens if it was positive. So here are the properties you want of such Lyapunov functions or progress measure. And let me write them down. You want an upper bound, so you want to say this, all of them are bounded, and it's very easy to see that any stochastic matrix, either rows or columns are sum to 1. The permanent is at most a product of the row sums or column sums, so it's at most 1. So that's easy. So we have an upper bound on this progress measure. The second is you want to show some growth of this progress measure, that iterations do something. And it turns out that it grows non-trivially. That's in order to establish efficiency. It grows non-trivially at every step, as long as you are not too close already to your goal. So that's the green star there. And this turns out, I'll show it to you in a second, but that's just arithmetic mean, geometric mean inequality. And the last thing is that you don't start too low. If the permanent is positive, then it's not too small, and that's also easy to see. So I want to show in the next slide this proof of this. So that's one proof you'll see. But I want to stress that in this baby case of matchings, the proof that this algorithm converges in short amount of iteration is really small. Right, so if the lower bound is exponential and we progress multiplicatively, of course we'll converge in polynomial time. Okay, so the last step is easy in this case and will be hard as we go to non-commutative singularity, and the other cases will remain easy. So we'll see that a little later. I just want to say that. I find this in itself a really neat algorithm for perfect matching that nobody learns in college, and it's as simple and maybe simpler to program. It's just 2 lines of code, anyway, I'd like to advertise this if you would like to teach it in your courses. Okay, what's the proofs of the statements there? So again, this evolution creates a sequence of matrices. The matrix will start with A, and then A1, A2, and so on in the iterations. And we pick the permanent to be the progress measure. I already told you why the, case 1, why all of them are bounded by stochasticity. Number 3 is simple because after, let's say it's stochastics, row sums are 1, then if there was a diagonal of 1, this diagonal is not, let me assume it's a 0-1 matrix. The same analysis would work for any real matrix, but you just have to change what you mean by n, the input side. So let's assume it's a 0-1 matrix. So these entries are at least 1 over n, so the product is at least 1 over n to the n. So you have an exponential lower bound and the initial matrix, and then to analyze the second step, let me just rename, because instead of saying AI and AI plus 1, let me just say B and C, the 2 subsequent matrices in this list. And let's say we already scaled the row, so B times 1 is let's call it vector V, is all ones vector, and if we look at the column sums, we see some vector U. That's the current column sums in B. And we see what happens after 1 step of scaling and when we get the matrix C. So, okay, this one I mentioned before. Okay, so what is the permanent of C? We want to see how the permanent of, the next step changes with respect to the previous one. Well, we scale, right? Multiply by the product of 1 over the UI, the column sums. The permanent of B. It's nice to, the permanent changes in a very predictable way under scaling. That's one reason to use scaling. Okay, and now you use the arithmetic mean, geometric mean inequality, and you replace this product by the sum. And the last observation is that, what is the sum of the UI? The sum of the column sums. It's the same as the sum of the row sums, so it's n, so you just get 1 there, right? So you just have this inequality. So the permanent does not decrease, at least in iterations. But we wanted more, we want an increase, as long as we are not too close. And the same AMGM will tell you that if the sequence is far from uniform, you get a gap in the AMGM. So you just apply this, and yeah, it gives you the result. So it's very easy. That's a very important message. Okay, good. So questions about this? Very simple analysis. Okay. I want to mention, we hopefully will come back to this at the end, that everything works in exactly the same way if you care about non-uniform scaling. So you don't want a doubly stochastic matrix, but you want the row sums to be some vector p and the column sums to be some vector q, right? And it turns out that this is an interesting problem, and it's it relates to maximum flow, and it captures lots of marginal problems if you think about it. If you think of a matrix as being some kind of a measure, a two-dimensional measure or two-dimensional distribution, and you're asking about making the marginals, prescribed marginals, you can think also of high-dimensional version of this. You just want to get some multivariate distribution to have prescribed marginals. So it's a very general kind of problem, and there are quantum analogs we may discuss. So in the non-uniform setting, the same alternate minimization works, at least for this two-dimensional version. So we'll, the same heuristic is quite powerful. Okay, so now we are done with the baby case, and I want to move to the real case, which is a non-commutative singularity and its connection with operator scaling. So many ideas appeared in Gurwitz's paper following that same paper I mentioned with Samorodnitsky and Lineal that I just described. He saw that one can generalize it and maybe approach singularity. And then the paper from about 5-6 years ago that actually gives the algorithm. So I want to describe what Gurwitz did first and then what we did. Okay, so I want to, before that, just have a very caricaturistic picture of what is, a quantum extension of a problem. Basically, there are certain things that happen in lots of quantum extensions. This here I'll describe the extension between matrix scaling and what will become operator scaling. The input matrix scaling was a non-negative matrix. You go up in dimension in quantum settings, so we'll have a tuple of matrices. This will be or a tensor or an operator. You move from L1 to L2. Typically, there's a very natural notion of double stochasticity, which is written on the right. So it's rather than multiply by the old ones vector, you just sum up AI dagger, and you want to get the identity. And similarly on the transpose, you don't have to remember this. Scaling was multiplying on the left and right by diagonal matrices, which are basically vectors. Again, you go up in dimension. In operator scaling will allow pre and post multiplying by non-singular matrices in order to scale this tensor or operator. So this was just disconnected. Let me connect it to what we have been discussing. Here's what Gurwitz did. He said, we want to solve singularity, the Edmonds problem. So I remind you the singularity question. Again, you have a tuple of matrices, a tensor, and defines a symbolic matrix, and we are interested whether it's singular, symbolic, commutatively or non-commutatively. And his main observation is that a tuple of matrices, a tensor, can describe lots of things. In fact, we'll see many other things, but the first was, it's not just a linear pencil, a symbolic matrix, can also describe a quantum theoretic object called a positive operator, completely positive operator. It's basically the most general transformation that quantum mechanics allows. You have a bunch of matrices, complex matrices, let's say, and they act linearly on another matrix P. So if the input is P, what you get out is this sum AIP, AI dagger. This is how the tuple acts on a matrix. Okay. It's very, you can see from the expression that if the input matrix P was the positive semi-definite matrix, that so is the output. That's very important in quantum information theory because this matrices usually represent quantum states, mixed states. So that's what it is usually applied to. As I mentioned, there's a very natural sense in which an operator is doubly stochastic, and it has a meaning in terms of this operator. It really means that when you apply it to the identity matrix, you get back the identity matrix, both the operator and its transpose. So it's really the analog of row sums and column sums equal 1. So Gurwitz noticed that, and finally, so he saw a scaling problem here, and he asked whether, given an operator, can it be scaled? It's obviously a generalization. It's also formally a generalization of the matrix scaling problem. One can see that, but and he proved something really nice. So this is the operator scaling problem, and he proved something really nice. He said that if you cannot scale, if it's impossible to scale, this means that the symbolic matrix is singular in the original sense, in the commutative sense. And he wanted if and only if, and he realized that it's actually not true. So that's what, where it stood. But one thing that was important to us was realizing that, in fact, this operator scaling problem is equivalent to non-commutative singularity. The matrix is non-commutatively singular if and only if it cannot be scaled. Okay, so that's one connection, but let me proceed with what Gurwitz did. He said that, okay, we want scaling. Let's just, we have an algorithm. It's greedy alternate minimization. Let's do it. And in fact, one just needs to observe that solving half the problem, scaling either the analog of rows or analog of the columns, satisfying one of these two stochasticity equations is really easy by pre or post multiplying all matrices simultaneously with a particular analog of the row sums and column sums. You don't have to read the expression, it's just the same. So the algorithm is the same. It's suggested let's run polynomial a number of steps, these iterations, pre and post multiplying, it's just implementing alternating minimization in this more general context. And the hope is that, if we converge, then we say, yes, it's non-singular. Otherwise, we say it's singular. Of course, the right thing is to put non-commutative singularity here, which was not in his original paper. But that's, the hope. And the question is, why should anything work? So the first thing you need is a progress measure. And Gurwitz suggested one, very insightful one. Again, you don't have to remember this, will not be important, but I'll say it because it's nice and some of you will pick on it. It's a ratio of the determinants of the output and the input of the operator. And you take the infimum, you look at how small it can be. He tried also a quantum permanent first, and it was not quite as good. And this turned out to be the right one. And it at least satisfies what you want. So what I said before, non-commutative singularity by this equivalence means it's if and only if capacity is positive. So it satisfies exactly the kind of the analog of what happens with the permanent for matching. Okay, so we have an algorithm, and then what analysis to use? So what is suggested is let's use the same analysis. It's very easy to prove in the same way that this progress measure is upper bounded throughout the process. It's very easy to prove by the same arithmetic mean, geometric mean inequality that it grows whenever it has room to grow. And where it got stuck is in proving a bound, namely that capacity is positive, then it's actually, it's just exponentially, not worse than exponentially small. If this is true, then because it's geometric growth, it will converge in polynomial time. So this turns out to be hard. And this is really the main thing that was done in this work from 6 years ago. And the reason that, it was trivial in the case of matching, here, as I mentioned, this implies a polynomial upper bound. And the reason it's hard is that you need non-trivial input from mathematics. So we'll see all of this in more detail. I'm just highlighting that we'll need the fact that there is a group action in the background, and this capacity measuring is in some sense invariant or semi-invariant of the action. And to analyze, we need to understand degrees of invariant polynomials. So I'll define all of these. I just want to, maybe that's a good end to the first part, is that I mentioned that Gurwitz's insight was that a tuple of matrices can be viewed in many ways and leads to many problems. I mean, he mentioned the operator scaling. And it turns out that tuple of matrices is a tensor, appears in lots of places, and is the source of lots of problems. So I listed here a bunch of problems. I'm not going to read all of them, but you can see that they are in very different areas. I mentioned the one in quantum information theory, the operator scaling, because of the question Joel asked earlier. It's, you see the non-commutative algebra question here. This is really the word problem for skew fields. So it's really the most basic question maybe you can ask, whether a rational expression non-commutative variables is equal to another or is equal to 0. It's a question in invariant theory which would be key to the continuation. But another connection is you can ask a question. It turns out to capture a question in analysis which has to do with the Braska-Blib inequalities. I can talk about this later if we have time. The point is that all of them are equivalent, or more precisely, the first 5 are exactly equivalent. So natural problems in lots of areas have exactly the same answer. So a tuple satisfies one condition if and only if it satisfies the other in all these problems. So it's pretty remarkable, I think. The 6 is a bit weaker, but it's sort of a special case. But because of this equivalence, the polynomial time algorithm I told you about actually solves all of them, right? So we get efficient solutions to lots of problems in lots of areas. Some are absolutely fundamental problems in these areas, not arbitrary. Okay, so that's more or less, let's see how we are with time. Okay, 10. So we are going till 10:20 and then we take a break. That's the plan.
Yeah, I mean, I think the schedule says, 10:15 in your time, and then we.
Yeah, but But anyway, maybe it's a good time to ask questions, because now I'm going to go into invariant theory and start explaining these connections. Any questions?
Yeah, can I just have a question about the free skew field? I mean, can you say anything about what this thing is? Because it's a complete mystery to me.
Yeah, so I have a slide much later, but let me say this. What is, first of all, the field of rational functions in the case of commutative variables? It's you take the commutative polynomials and you close them, right? You to make them a field. And it turns out that all you need to do is just look at ratios of polynomials. right? So that this is a standard construction that we are all familiar with. What you want to do in non-commutative case is the same thing. You take the non-commutative polynomials. That's a very, it's a very simple objects. The only difference from commutative ones is that the order of variables in the monomials matter. So it's another vector space, and it's an algebra. It's not a field yet. So you want to make it a field. So you want to allow division or inverse. The question is exactly how to define this, because it turns out that for non-commutative variables, if you take if you write an expression and you take inverses and then you continue the expression, take another inverse, you cannot simplify it into a ratio as in the commutative case. There's a theorem that such expressions cannot be simplified. So there are expressions requiring arbitrary number of inversions. The field, the free skew field, is a field of all these inversions, of all these expressions. All expressions, I mean, that's one way to define the field. All these expressions, you just write formulas, expressions, plus, minus, times, division, or inversion over the field you have, under equivalence, under, when the two expressions are the same, then they are the same object. It is the same under the field axioms. And the question is, what is this set of objects and how to represent it? It's highly non-trivial. So I cannot offer you a really good, intuitive explanation of this. I'll give an example maybe later, and you'll see what sort of strange things happen in this field. But basically, just if the PIT question is, I give you two polynomial expressions or even rational functions in commutative variables, are they the same? In the free skew field, the same thing is with expressions over non-commutative variables.
Thank you.
Okay, so I want to talk about invariant theory, give you a very short introduction, just as much as I will need, so that the notions will be clear. I'm sure some of you have seen this, some of you didn't. So what is invariant theory? It's a study of symmetries. Symmetries are captured by group actions. And here are some examples. So we can take the vertices of the graph and permute them. Here the permutation, we act by the permutation group on the vertices. We can hit the cue ball in a billiard table, and it sends it's an evolution of the configurations. Here the group acting is basically time. As time evolves, we change. Here's another one I really like. You take shapes in the plane, polygonal shapes, and what you are allowed is to cut with straight lines and reorganize the shapes, let's say, never overlapping them. And that's also some kind of a group. And what you are interested, of course, this is somehow, you can think of it as the dynamics. The group acts on this on an object. So you are interested in the orbit, where are all the places that a particular object can go under the group action. And even though things are changing, some things are not changing. It's very important to understand invariance of actions. So for example, in this polygonal shapes below, it's very easy to see that area is preserved. Whenever I do that, it turns out, and it's a theorem, it's a nice theorem, that it's the only invariant. So we are often interested in what are all the invariants of a given action. You can do it as an exercise, and then the next step you can try to ask yourself whether the same is true in 3 dimensions with polygonal bodies. Anyway, also in this physics example on the top, we learn in school that here there are exactly 2 invariants, energy and momentum. So it's also figured out in graph isomorphism. This nobody knows what's a good set of invariants for this action. I mean, we have now a quasi-polynomial time algorithm by Babai, but it doesn't give us invariants. Anyway, these are just examples. They are different than the examples I want to talk about. Those I want to talk about are linear. Move. Anyway, my screen is a little blocked. Anyway, we will talk about linear group actions. Linear groups are just think of groups of matrices. And I put this red star over X because one has to define, put various restrictions. These are reductive group actions, and the actions are algebraic, but you don't have to remember any of this. Just think about just matrices acting on a vector space. So there are two parts to this theory. One is algebraic and talks about the invariants that happen to be polynomials. And one is geometric or analytic that I'll get to both. Talk about the geometric aspect, the space of orbits, and a certain non-commutative duality that I'll explain. But anyway, there's a beautiful interaction between the analysis and the algebra in this study of linear group actions. Here are some basic notions that we will need. So that's a one-slide introduction. We have such a group of matrices. You can think of SLN or GLN or any subgroup of them acting on a vector space. Let's say it was f to the k over some field. I mean, most of what I'll say is, the theory is most developed over fields of characteristic 0, but some of it is known over finite fields. So if it acts on this vector space, it of course acts on polynomials in variables in this coordinate. So this is the action we care about. Now, what is the orbit in this case? Well, the orbit, I said, it's everything a point, a vector can move to under the group. Okay, so that's the orbit of a point V. And because we are working over, let's say, the complex numbers, we'll care about orbit closures as well. So you close the orbit, you take all the limit points. So it's a set of points, you take all the limit points. It's a much more natural object, in fact. Okay, the second notion is an invariant ring. So all the invariant polynomials of this action. So as I said, the invariants, the things that do not change under such actions are polynomials. And we want to collect V sub G is a collection of all polynomials that remain invariant under this action. So all polynomials P, so that P of GV is P of V for all elements of the group G. Okay, so here are some examples that you know. So suppose a symmetric group acts on an n vector by permuting the coordinates. Of course, it's a linear action. In a smaller audience, which is a live talk, I would ask the audience to tell me what are the invariant polynomials. Here it's clear, it's just all symmetric polynomials. These are polynomials. The symmetric polynomials will not change if we permute the variables. And moreover, we know that all the symmetric polynomials are spanned as an algebra by the elementary symmetric polynomials. So it's a very nice basis to this invariant ring. All the elementary symmetric polynomials are polynomials of degree at most n in this case. Here's another one that you know. Here is the group is the group of invertible matrices over F squared. So and it acts on matrices. So how does this group act on a matrix V? It just pre and post multiplied by a non-singular matrix on the left and on the right. You see that's more relevant to what we've been discussing. And again, easy riddle is what are invariant polynomials in the matrix entries, in the the entries of V that does not change under this action. And the answer is the obvious one. The determinant doesn't change because the determinants of R and C are 1. And that's the only thing that doesn't change. So any other invariant is just a polynomial in the determinant. Okay, so these are simple examples. Also here you see that the degree is small. That's this invariant ring is generated by a low degree polynomial, and the question that was studied in the 19th century extensively by lots of people was finding degree bounds or finding generators for invariant rings for a variety of actions, since Cayley invented invariant theory. And lots of things were known, lots of things were open, and then Hilbert came and in his famous papers from 1980, 1983, sorry, 1993, proved this theorem, that all these invariant rings are finitely generated. So in particular, you can bound the degree by which they are generated. For those, many know this paper. This was revolutionary. It really created the field of commutative algebra and contains lots of major results like the Nussbaum theorem and the finite basis theorem. It's sort of amusing to know that he was working so hard just in order to prove this theorem. Of course, after that, both he and many others realized there are many other consequences to these theorems. But yeah, he was interested in showing that every invariant ring of any polynomial linear actions like this is finally generated. And then people started studying degree bounds, and I'll talk about this a little later. What's the smallest degree in which you can generate an invariant ring? And it will be important for us for the analysis of this, the algorithm I showed you. The last notion I want to mention, and it will come up, is the null cone of a group action. So what's a null cone of a group action? It's all the elements in the vector space that look like zero. Right, zero has a special, it's sort of special. If you consider only homogeneous, invariants, which you can and should, then they all become zero at the point zero. So you just wonder what are all other points that are equivalent to it. So they become also, they take the value zero on every invariant polynomial. In the orbit space, these are like all points that look like zero. And when you study, the orbit space of some action, you would like to sort of projectivize it and sort of mod out by this null cone. But it doesn't matter, this intuition. Anyway, it's a very natural subset of the vector space, the null cone. And this is an algebraic definition and a central connection. It's an algebraic variety. And we'll be interested, you'll see later, in membership in this algebraic variety. But a central connection, this analytic and algebraic connection, was made by Hilbert and sort of spelled out by Mumford, is that there is an analytic definition to the null cone. So a point is in the null cone, V, a vector is in the null cone, if it is the limit. So if it's in the orbit closure, right? If zero is in the orbit closure of V, in other words, if you, by group action, you can approach zero by applying the group elements to V. And this is the same as just asking whether the norm can be made arbitrarily small. So you just ask whether you can make the norm of some points in the orbit of V as small as you like. We'll see examples of this very soon. In fact, all the problems we looked at are null cone membership problems, it turns out. What are the null cones in this example? Well, the first one, symmetric group, is just a finite group, so there is no limits, and the only element in the null cone is the zero vector. Here it turns out that it's a very natural set. It turns out that the null cone of this action on matrices, left and right multiplication, is exactly the set of singular matrices. It's an easy exercise, you can prove it. It's just to point out that null cones are very natural objects, and there are many other, nilpotent matrices are, the null cone for action, for the conjugation action, and many other things you've seen turns out to be null cones of natural action. So many definitions you've seen in mathematics that never mention any symmetry or any group actions can arise by looking at them this way. And injecting symmetry into the study of anything is always worthwhile when you can do it. Okay, so I said it's already a null cone membership is given a vector. Is it in the null cone? As it will turn out, you will see that it captures the scaling problems we've seen. It's dual in a very precise sense to the scaling problems we've seen. And it comes up in lots of problems. I mean, many problems we've seen that have no symmetry in them in many areas are actually null cones. So understanding the complexity of null cone membership problem is really important. Okay, so let's dive into this. Or maybe not. Yeah.
Avi, would it make sense to take a break?
Yeah. I was just going to say, yeah, and actually now it's a great time to take a break.
So perhaps I see that the schedule had time for questions now, and then we take a little break.
Yeah, sure. Questions are invited anytime. Yeah, any more questions about what we've seen?
So questions from the audience. Anyone? Please go ahead and unmute yourself if you'd like to ask a question.
So I have a question.
Yeah.
At the very beginning, I wonder what type of argument you use to show that if you have p-time algorithm for p or for singularity, then you have something like p is not equal np.
Yeah, it's a very good question. So here is the type of argument. Let me first tell you that results of this type, implications of this nature, trivial ones, you basically know. So let me give you an example. You look at p, at np, and at exponential time. Okay. Then np sits in the middle. We don't know whether it's equal to one of them, but it doesn't equal to both because polynomial time is weaker than exponential time. So if we prove, for example, that np equals p, that's an algorithm, then we also separated np from exponential time, right? We prove the lower bound.
Mm-hmm.
And the source of this result comes from, the fact that p and exponential time are different. That comes from a diagonalization argument. Okay. Now, what happens in the result of Cabanas and in Pagliazzo is a very sophisticated use of, partial input is a diagonalization argument which proves that the non-deterministic time hierarchy. I talked about the deterministic time hierarchy. There is this is one input. This was known, of course. That is going to be one input. And what they need to show is that an algorithm for this particular singularity problem will enable a violation of this, separation. So it's of the same nature as before. Now, in order to prove where does a deterministic algorithm for singularity problem plays a role, it plays a role in the following thought experiment. So suppose there was a small circuit computing the permanent. The permanent is, just a permanent polynomial. Suppose there was a small arithmetic circuit computing the permanent polynomial. If there isn't, then you already prove the lower bound. This is in fact the lower bound you prove, right? If there isn't, then so you are happy. And if there is, the way the singularity statement is going to be used is just from the existence of a circuit to find a circuit. And you are allowed non-determinism because we are talking about the non-deterministic hierarchy. So you would guess a circuit, and then you would like to verify that it's correct. And verifying that it's correct is going to use, basically this downward self-reduction of this problem. So you assume you have circuits for all the input sizes, and to check that you can, your circuit for n by n matrices permanent is correct. You assume you have it for n minus 1. You expand by a row, let's say, they're permanent, and this becomes a polynomial identity testing, right? You have circuits, and you want to show that some circuit is computes or the two circuits are equivalent, and here you use this algorithm. That's the place where it comes in, and you need deterministic, or at least a non-deterministic algorithm. This randomized algorithm is no good in this context. This randomization can be exponentially more powerful. So that's a very high level, quick description of what's going on. So I'm sure that some people it can help and some others it cannot.
Okay.
But let me summarize that it uses some sophisticated understanding in complexity theory, several of them, and putting them together in a clever but really relatively simple way. Yeah, more questions. Okay, maybe we'll take a break. Joel, maybe I'll go and make myself some coffee.
So, should we reconvene in, let's say 20 minutes? Is that
10:45?
Yeah, 10:45. And for those of us in Europe, it'll be on Paris time. Let's say it's going to be 4:45.
Okay, great.
Okay.
So yeah, I don't know when you want to start, but you tell me.
Okay, let's just wait perhaps 1 minute, because I see we're still waiting for people to come back. Let me just all right. Let's see. Okay, well, I think we should continue.
Okay. Okay, so I want to tell you now about sort of integrating, encapsulating what we've seen and generalizing it. There'll be 2 rounds of that. And the first one, we are trying to understand what other problems we can apply the same tools that use similar algorithms like this alternate minimization algorithms. And I'll first remind you, I mean, we've seen alternate minimization, some examples. I want to tell you how broad this is, so I'll take a short detour just to tell you about some other problems that are of this nature that are used. This kind of heuristic is used all over the place in optimization, machine learning, statistics, to solve problems that don't admit obvious efficient algorithms. And the nature of all of them is that you want to solve, optimize, or sample something that is a multivariate function. It has several parts, like we saw problems with 2 parts, where it's really complex. But if you fix all but one of the parts and let the objective be solve it for one variable, one of these coordinates, then it becomes a simple problem. And these examples were the same. And there are many examples where it's used. I'll just show you the variety. This, the heuristic suggests itself, but we don't understand what it does exactly. Here's one very old example, just computing the distance between two convex sets. It's an idea for Neumann. It can be even considered infinite dimensional sets, but you want to compute the distance between these two complex bodies. And you can do what is called alternate projection. Just look at the sequence of points, one in each, that where you can start anywhere, compute the closest point to it in the other body, then compute the closest point to it, the closest point, and so on. Yeah, this is something that always converges, and we don't know exactly how fast in general. They're a very simple idea, and it's the same type of algorithm. It's a very different example. The famous Nash equilibrium problem. You have a two-player game, so two pair of matrices for two players, and you want to find a stable behavior, probability distributions that correspond to, if you think of the rows and columns as being strategies to the two players, these distributions correspond to an equilibrium, namely each is the best response to the other in terms of the payoff to each player. So it's written formally here, but Nash famously proved that there's always a Nash equilibrium, part of his Nobel Prize. And how do you find one? It's a hard problem. We don't really know. And there's sort of an heuristic. I mean, there are better heuristics, but anyway, there's a heuristic that says, okay, let's start with any strategy for one player, find the best response for it, etc., etc. Each is an easy step, and it does. This particular heuristic doesn't always convert, but we know that sometimes it requires exponential time, and yeah, we don't know a good algorithm for this problem, but this heuristic is natural in this context as well. And another example, just to show you, it's not just about optimization, it's also about sampling. We routinely use it maybe without thinking that this alternate minimization. Here's an example. You want to sample from a distribution that's complex over a large product space of many parts, and you want to sample from it. Maybe it's a complex distribution. So one idea is to fix all coordinates and just resample one coordinate consistent with the distribution. Here's a very familiar example. You want a random coloring of a given graph, a uniform over all legal colorings. And one way is to start with the one legal coloring and just resample one of the colors consistent with its neighbor, so it continues to be a legal color. This is another manifestation of this heuristic. So it's a very general heuristic. We don't understand it, but we saw that in this algebraic setting, at least in two examples, we do understand it. So let's go back to these two examples that we saw. Here, the alternate minimization is on groups. Really, realizing that these are problems on groups allows inviting invariant theory and making use of these results. So I'm reminding you, this matrix scaling and operator scaling problems. We use alternate minimization in both. The action we took, namely scaling matrices with pre and post multiplying, and same in the operator scaling. These are really group actions. In the left, it's a torus group, it's a diagonal group, and the right is GLN on the left and right. And we look really at an orbit of the given input. That's all we are doing is moving along an orbit of the given input, the vector we are given. The analysis used so far very different potential functions to analyze the two algorithms, and we'll unify this too soon. And these were scaling problems. I also mentioned the scaling will become dual to the null-con problem, so we'll see that too. So again, I'm stressing the algorithms, this particular alternate minimization algorithms happen or evolve along a group orbit of the input. So we want to generalize this, and there's a very natural way to do this. Here the framework will be that we operate on tensor maybe in k dimensions. We have a product of groups, k groups. Each of them, let's say, is all inversible matrices or just diagonal matrices, but it's more general. And you act on this vector. Every group acts on the ith group acts on the ith dimension. So really generalizing everything we've seen in the natural way. And you can ask, given a vector such a tensor, scale it. This generalizes as well. It means making all marginals uniform. I will not define it. And a general theorem that we proved is that this algorithm works in this generality. So alternate minimization, you just move between the dimensions and scale them and continue as long as you're if you run polynomial time, then you approach a scaled version if it is at all possible to scale. And I'm stating this both because it generalizes what we've seen, but also I want to, until now I didn't give you sort of a hint of the analysis and where it uses the invariant theory. Here I want to do this in this setting. I want to stress this is a non-convex problem. In fact, the domain is this set of groups. It's a function of these groups. You are looking for a group element that scales the input, and nevertheless, despite the fact that it's very non-convex, we get a simple heuristic makes it it's provably efficient. Here again is a statement. The goal is scaling an input tensor, or else, I mean, I told you they are dual, well, make it precise, or else determine that it's in an algorithm. These will be the only two possibilities. And this captures lots of problems. We've seen in the 2 dimensions, the matrix scaling, the operator scaling. In higher dimensions, it captures problems in representation theory, in quantum information theory, in combinatorics, and there are really more examples. So it's a very natural set of problems, even though we define it just to suit what we know how to do. And for all of them, we have this algorithm, this heuristic converges in polynomial time. It's very important to stress that this polynomial time is not always enough to say to have a a real polynomial time. This epsilon sometimes needs to be exponentially small, so that is not always enough. So when do you know that you are scaled? In the examples we've seen, it was enough to get within a polynomial of the scaled version, but in some other problems it may not be enough. But the main point is that the analysis of this algorithm in this very general setting is the same. I mean, it's a 3-step analysis. You pick a potential, and I want to stress here that it turns out this one of the understandings we arrived for this invariant theory framework is that even though we had before very specific tailor-made potential functions, it's enough to study the L2 norm of the vector. This is really all you need to do. It's very easy to see that it's it's bounded by something by 1, let's say, and one can show that it grows by the same arithmetic mean, geometric mean every step, so that these 2 parts were always easy, and it's easy here as well. And the main problem, like we saw in operator scaling, was how to prove that if a vector is not in the null cone, it cannot be scaled. It can be scaled. Then it is already, its norm is large enough to guarantee that the convergence will take just polynomial time. So here we need inputs from invariant theory, representation theory, etc. But I want to show you the gist of it. Okay, so that's the next slide. So what does the what do invariant polynomials have to do with this? So we want to show that if a vector is not in the null cone, it cannot be pushed to 0 by the group, then its norm must be big. So I remind you that a vector is in the null cone if it is 0 on every invariant polynomial in the invariant ring. Okay. So what does it mean? What is the negation? It's not in the null cone. Then there's some invariant polynomial which makes it non-zero, and we can assume this is a the coefficients are integral. So in order to bound the norm, we are going to bound two other things, very natural things about polynomials. We don't know this polynomial. We are not going to search for it. There are doubly exponentially many or more. As we just use its existence. So what do we want to know? We want to know that there is such a polynomial of relatively low degree, let's call it D, and relatively low height. Height is the size of the largest coefficient in it. Okay, and then the inequality we are going to use is a very simple one. We want to bound the, look at the sandwiching the bound of this particular invariant polynomial that doesn't vanish on V. It's an integer polynomial, so it's at least 1. On the other hand, it's just the number of coefficients times the size of the largest coefficient times, you multiply entries of this vector, so it's a norm, at most a norm of V to the D power. So if D and H are small, then this will be small. So what small means? Well, for all these actions, there's a very general bound by Dirksen showing that the degree is most exponential in the number of variables. That's a very important result. So this is the best general result after the set of work started by Hilbert, the finiteness bound. And to bound the height, it turns out that at least for certain groups, which are, there are others. Cayley, in his first paper in 1850 on really introducing invariant theory, described this amazing process which he called the omega process on sort of an algorithm to generate a basis for the invariant polynomials in any particular degree, and implicitly it can give bounds on the height, on the size of coefficients, which are roughly D to the D. And if you plug these two pieces of information in, you get a lower bound on the norm of the vector, and if it's exponential, you get back, you get this top row, this exponential lower bound on the norm of the vector. So I'm stressing we use only the existence of this invariant polynomial. We didn't use the, we didn't need to find it, just use the known, or well, sometimes we had to prove bounds on this degree and height. So it's a proof, but there's a sort of a higher level question that is, it's a non-convex problem. Why does such a simple algorithm converge? There has to be an intuitive reason. What connects? I kept mentioning the scaling and null cone problem, and also, this solves a nice class of problems where alternate minimization fits. But is it essential? Is there a more general framework that allows us to deal with, let's say, the actions of not products of groups, let's say conjugation, and there are many other examples. And the answers to all of them will be the same. We just have to understand something. So I'll explain this next. So before that, I want to ask if there are questions. Okay, shall I continue?
Yes, please.
Yes. Okay, so now I want to tell you about a really key element from the analytic side of invariant theory, which is this non-commutative duality. And I'll explain something about these notions of geodesic convexity and the moment map, etc. Okay. So we are back to this picture of our two problems, and now I want to stress something else. So we had, the way we talked about them so far is we had a goal, let's say, scale matrix or operators or higher dimensional tensors. And then there was this alternate minimization algorithm, and it was analyzing it using the particular potential function. We saw that actually minimizing the norm is a general one. But I think for this, the next step, it's good to switch the analysis and the goal. So rather try to minimize the potential function and see what we get. So we make this the goal. Okay, so let's look at this. Again, we have a group. Now it doesn't have to be a product group, just any linear group acting on a vector space. And the goal is minimize the norm of a vector in the orbit, right? So over all elements in the group G, you look at the minimal norm of G times V, minimal L2 norm. Okay, that's a new goal. This is what was used in the analysis. Now think of it as an optimization problem, right? You find the lightest vector in the orbit, like in this picture, the vector closest to zero in norm. So optimization, and I mentioned it's a non-convex optimization problem. Okay, so that's what we want to do. And if the limit, so in particular, we may ask whether it approaches zero, and we know that we define is an Alcon problem. So from the certificate point of view, from the NP and co-NP type of language, certifying that the limit is zero is intuitively easy, right? I mean, you find a sequence of elements that shows that it gets closer and closer to zero. It's just intuitive level. But how do you certify that it's far from zero? Suppose it's positive, separate from zero. It's not in the null cone. How do you certify this? Of course, we know that there exists an invariant polynomial that's not zero on this point, but searching it can be doubly exponentially expensive. So we want a better certificate, and this is provided by a central theorem in this field. It's a Kemp-Ness theorem. And they say the following: the value f of v, so the minimal norm, is positive, is away from zero, if and only if something else is zero. This something else is the moment map. So the moment map is zero. There is some v star in the non-zero vector in the orbit so that its moment map is zero. And the moment map you can think of as a gradient. So first, whenever you see a theorem like this, it does sound like familiar duality theorem. Something is positive if something else is at least zero. It's in fact a vast generalization of linear programming duality. In a sense, what you'll find, the certificate is a sort of separating hyperplane that separates this V star from zero. In fact, that's what happens if the group acting is the diagonal group, namely a commutative group. What is new? I'll have more on the next slide, but it's basically, you should think of it as a gradient. Okay, so the gradient of this function, the norm under the group action. And now that, if you see this, it sounds like, it should remind you maybe of normal convexity. Before that, it turns out, and this I will also show you, that the minimization of this gradient is really a scaling problem. And so making it zero is sort of dual to minimizing the L2 norm of the vector. There are dual problems. One is 0 if and only if the other is non-zero. And this theorem, the Kempner's theorem, suggests, I mean, if you see what it says that you cannot approach 0 exactly if the gradient is 0. The gradient is 0 at any non-zero point. So this local optimum to minimizing the gradient is a global optimum. If it's 0 somewhere, you cannot push V to 0. So this V star is the global optimum of this function f. And this again, should be familiar from normal convexity theory. And this will lead to algorithms as I'll show you soon. So I want to just elaborate a little bit, not much, about the previous 2 points. So yeah, this I mentioned already. So the fact that there is some convexity in the picture from this Kempner's theorem sort of intuitively at least explains the convergence of such a local greedy algorithm like alternate minimization. Right? It's greedy, so it can only lead to a local optimum, and nevertheless it's global, so this is guaranteed by convexity. And again, it suggests algorithms that I'll show you, these extensions of convex optimization. Okay, so what is a moment map? You should have this picture in mind that is drawn there, which you can think as Euclidean. I mean, it's really the same intuition. Maybe I'll say a little more about it. The moment map, just like a gradient, is a gradient of the norm of our function when you look at the limit around a group action which is close to the identity element. This is what we do in the Euclidean case, right? This is what we mean by, like, in the real analysis, you perturb an input and look at how it changes, its norm changes, but here it's just its value around when this is close to 1. And so it's a linear function. For any group, this is a linear function, this gradient, this moment map. And you can ask where it lives. I mean, where does this linear function live? What is the parameter space? Well, it lives in the tangent space to the manifold, which is the group. And so formally, it lives on the Lie algebra of this group. You have to do various things. I'm not going to get into this. But it's, all the intuition you have from the Euclidean domain carries out. There's a natural linear space, which is this Lie algebra, and it parameterizes the gradient, parameterize the directions in which you can perturb any point. The main word moment comes from momentum. It comes from physics. That's the origin of this, and it's studied also in symplexic geometry. It's a very basic notion. And as we said, the minimization of, so we have another minimization problem, minimizing the gradient or the norm of the gradient, and when it's 0 exactly when you cannot make any element in the orbit close to 0. So they are dual. So that's a connection that's coming from this duality theorem. So this is a moment map. So it's really like a gradient. And this connection to scaling is, I can show you by example, and you can at least believe that it's true in general. Once you, of course, scaling is not a word that's automatically defined, but on this context, it's very natural. So here in these 2 examples, we saw these actions, and one can compute the moment map for these actions. And I'm not going to do the computation. I'm going to tell you the result. This was the scaling problem. And if you compute the moment map, you will see that of this group action, just by the definition, in the left side, you will get exactly the difference of the row sums from the all ones vector and the difference of the column sums from the all ones vector. So that's 2 vectors of length n. This will be the gradient. It's a length 2n vector. In the case of the operator scaling, it turns out that the tangent space is all Hermitian matrices. And so you get two Hermitian matrices. And if you look what they are exactly how far this tuple of matrices, this positive operator, is far from being scaled, from being doubly stochastic. So scaling problems come up, naturally. We didn't have to know they existed. You just minimize the gradient and out come scaling problems. So that's for these two examples. And as I said, in general, minimizing the gradient can be viewed or can define scaling problems in a natural way. Okay, so the moment map is 0 if and only if V can be scaled. It cannot be pushed to 0. Okay, so that's about the connection, this duality between the moment map, minimizing the moment map and the L2 norm. And now I want to talk about how it leads to extending the framework of convex optimization to this non-commutative setting. So these things were studied, of course, for a long time. Geodesic convexity, Gauss, Riemann, many others studied convexity in these in Riemannian manifolds, and the notions are well known. But geodesic shortest distances on manifolds is well-studied subjects, and even algorithms were studied for a long time. Here, for this type of problems that we are doing like this, the norm minimization and moment map minimization, what we get is actually algorithms with quantitative bounds, which are analogous very much to the ones that exist in the standard convex optimization. So I want to talk a little bit about that. So just, you have the analogy. I hope everybody has seen some, gradient descent or, just standard convex algorithms. So on the left, I have the commutative setting, which is basically the action of some commutative groups, just multiplying by constants, which is what happens in real analysis, and over the Euclidean domain. And on the right, I have what happens when you act by some non-commutative group like GLM. So what is the direction in space? The direction in space is in the left side, it's a vector, it's this diagonal of the matrix. And we always think of an exponential. It's very convenient when we want to write something close to 1. So vector H specifies direction, and it's an element of the diagonal group e to the h, where on the diagonal we put the entries of this vector. And in the case of non-commutative setting, it's the same thing, but you put a matrix, a Hermitian matrix, to describe the direction. That's what I said before. So the tangent, is in the case of Euclidean space, you can expand this e to the h around 1, and basically the linear term is what we care for derivatives. And in the non-commutative setting, it's the same thing. You expand the exponential, exponential map only with matrices, so it looks the same. And what is a geodesic? A geodesic is it's the shortest distance. You can think of moving from a point in a particular direction at unit speed, and where do you get to? In Euclidean space, it will be a straight line. You keep going straight, and like in the direction h, as t grows from 0 to whatever. On some manifold, especially like the one here, then you have start from a group element, and then you evolve by multiplying it by e to the th. So it will be, it will be in general some curve. But along this curve, this geodesic curve, that's how you measure distances. And what's important is that in both cases, this function on the group, this function when you look at it as a function of the parameter t, the time you move along this curve or this geodesic is convex in both its settings. It's in both its settings, it satisfies. It's very easy to prove. I mean, just really easy to prove if the function we look at to minimize is this norm, the norm of the vector under such perturbations, e to the th, h capital or small, it's the same thing. And the definition of convexity is the usual one you are familiar with. It's just that instead of going along a straight line, it goes along the curve, whatever it is. So this convexity suggests using the type of algorithms that we are familiar with, also for non-commutative groups. I mean, we are at a point we want to minimize the norm, and we just move in the direction that is, the negative of the gradient, according, in some step size that it's important to choose. So the first order algorithms, you just, you are at some point and you just move a little bit in the direction of the moment curve, which is specified. This constant you knew, it just depends on the smoothness of your convex function. And similarly, you can study second order approximations. If you have access to the Hessian of the function, then you can approximate it by quadratic and get fast convergence. And basically that this norm minimization problem which we just defined, this converges always because of this convexity. And we want to show how fast it converges. So I'll tell you what we know. So again, this works for general groups. It doesn't, general group actions doesn't have to be products. It doesn't, we don't need alternate minimization. In fact, alternate minimization is often viewed as a special case of gradient descent, where the step size is given automatically by optimizing in one coordinate. But in general, you don't need this. You just do what I said in the previous slide. The problem is, we have this action. We are given a vector and some epsilon by which we want to approximate the minimum of, well, one of two functions, either minimize the norm along the orbit or minimize the gradient along the orbit, the moment map. We said they are dual to each other, but when you talk about approximation, they are not, there's a quantitative duality you want to, approximate duality that you want to establish, which we do. Anyway, so these algorithms work by having access to the action and to the function with this minimization problem, and to some derivatives of the function. If it's a first order, we get access just to the first derivative, to the moment map, and we do just exactly what we said. And it turns out that in this very general setting, you get the same result as in the Euclidean domain. It's polynomial convergence in 1 over epsilon, the number of iterations to getting epsilon close to the minimum. So it's completely analogous. And also in the second case, here it's the algorithm needs to be more sophisticated. It's some variant of the what's called box constraint Newton method. But basically, you do approximate your function by a quadratic. You have access to the Hessian. And like in Euclidean domain, you get convergence that's exponentially faster. You can converge in a polylogarithmic number of 1 over epsilon iterations. A big question in both the classical setting and this setting is what is hiding in the big O notation. And of course, in all cases, it depends on how convex your problem is. I mean, the more convex it is, the faster you get. So there are parameters that are, come from the data. The data is the group action. So there are, representation theoretic parameters that are associated to an action, which control the smoothness of this convexity and give you, at least in principle, gives you these constants or bounds on these constants for these algorithms. Maybe I'll stop for some questions before I tell you like the last bit. So summarizing this, this setting, because of the Kempner's theorem and convexity in this non-commutative setting, in principle, you should expect, and in fact, you get analogs of the convex optimization framework results in the, extended to this, to Riemannian manifolds.
So I have a simple question. Maybe I misunderstood something on previous slide.
Yeah.
You had, could you show it?
Previous slide, which one?
Yeah, just previous slide. Yeah, here you said that on this commutative case, this G to D times E power TH is a straight line?
Yeah.
Or...
Well, we look at the line above it. It's really, yeah. So the tangent space is a straight line. In the Euclidean space, the tangent space is in the space. So you don't need to curve. You don't need to sort of project back to the manifold.
So you say tangent space is a straight line. Uh-huh.
Yeah. And also the geodesic is a straight line for this very reason.
Aha, so in the non-commutative case, even the tangent space is a curve.
No, the tangent space is always Euclidean. Tangent space is always Euclidean, but if you go along it, you get out of the manifold and you want to stay on the manifold. So you have to project back, so sort of continuously. So that is what is getting you curve. You want to define geodesics, so ways to connect 2 points on this curved space. And what you do is you start moving along a direction and you keep projecting back to the manifold and continue doing it, but along the same direction. So H is fixed in this. So this sort of exponential map, it's really a natural extension. Of course, I realize I'm going to, to another area that is wide, and if not familiar, it may not seem intuitive, but it is really the natural way to extend what we know from real analysis to this setting. I mean, just have to understand the tangent spaces along any point of the manifold, and this leads to a natural definition of what geodesics is, or what at least a natural direction from a point in a particular direction would be. You just start it, and then you continue going along. Keep, if it was discretized, you keep stepping out the manifold, projecting, continue stepping out, project, and so on. This gives you a curve, and for all the points on the curve, this is the shortest point in the natural Riemannian metric on this manifold. Here we have the manifold corresponding to, I just talked about manifold corresponding to the general linear group.
Okay, I see. Thank you.
Yeah. More questions?
Yeah, just like a basic question about comprehension. So these directions here in the non-commutative case, are they're elements of the Lie algebra of the group? Is that the case?
The directions are elements of the Lie algebra of the group. Exactly. That's what I said before. The
tangent... No, I'm confused because so why is this in this slide? Why is the matrix Hermitian? So the Lie algebra of...
It's a very good question. It's not clear why it would be Hermitian. It could be, yeah, but it turns out since so there are lots of things I didn't tell you. So basically, when you trying to minimize the norm, let's say under the action of the general linear group, you realize that you should do a decomposition of the group by polar coordinates, but the analog of what we call polar coordinates, because the unitary group, so it has these groups have a maximal compact subgroup. In this case, the unitary group, it doesn't change the norm, so you can factor out the action of the unitary group. And what is left is positive definite matrices. So really the manifold you are looking at is a manifold of positive definite matrices. And the tangent space there is Hermitian matrices.
Okay.
That's so I skipped like many.
Okay.
Yeah.
Thank you.
Sure. Okay, so let me tell you a little bit about more extensions and so the more beautiful connections to optimization, to polyhedral optimization. Mention more notions. So you remember in the beginning, I told you about matrix scaling, just the very basic question of matrix scaling, that you want to make it doubly stochastic. It has a natural non-uniform analog, which asks, I give you a matrix, I want the row sums to be something and the column sums to be something, not necessarily all ones. These are non-uniform scaling, non-uniform marginal problems, and I want to talk about these problems in general. So let's see what we get. So again, back to the problem we were studying. First of all, we have a group action on a vector space, and we have the moment map defined as this gradient. And what we looked at so far is the null cone problem. I give you a point, a vector, and I ask, is there another vector in the orbit closure that has a zero gradient? And that's, we said, there are dual problems. I ask whether you can make the minimizing the norm in the orbit is the same as checking whether there is some point in the orbit whose gradient is the zero vector. This was uniform scaling. This turned out, I gave you some, I showed you examples that, matrix scaling and operator scaling are exactly of this type. They are equivalent to some double stochasticity in both cases. But I just mentioned that there are non-uniform scaling problems, and they turn out to be the same question, only that you are asking, is there a point in the orbit with some prescribed value? So this moment map or the gradient, you want it to be a particular vector p, as opposed to being zero. This it turns out that these are all the non-uniform scaling problems, and they are, you can think of them as marginal problems. You're giving them, some kind of a distribution, or this vector doesn't, some linear conditions on the marginals, because the gradient is a linear map, right? So you're asking whether there's any point in the orbit which has this value. And this leads to something very, I find amazing, given that we might be interested in such non-uniform scaling problems, we might as well define all possible vectors P that can arise as the gradient of some point in the orbit. So here is the definition. Delta of V is a set of all P, all non-uniform values we may want to achieve, such that some point in the orbit or in the orbit closure has this particular value. So the gradient is exactly P. Okay. So what is this set of all possible gradients? I mean, you can think what it means. What kind of set can this be? It will not be difficult for you to see that in the case of commutative actions, torus actions, this will be a polytope. I mean, this in fact will be, not almost, all commutative actions on vectors can be viewed as just scaling actions on polynomials, or Laurent polynomials. And the set of all possible gradients will turn out to live in the Newton polytope of this polynomial. this is not hard to see if you think about it. But now we are in the general case of arbitrary group actions, and I find it really amazing that this sequence of understanding, something starting with Atiyah for torus actions interested in problems in Hamiltonian dynamics, and then in very general terms done by Kirwan, Brion, and others, this set of points of vectors is always a convex polytope. Okay, I put a red star there also when I talked about all gradients. One has to, normalize, remove redundant elements in these gradients and so on. But essentially, these are all gradients, and the set of all gradients is just a set of points in space turn out to always be a convex polytope. Why do I find it amazing? I mean, until a few years ago, I was taught to believe, or just from experience, I thought that polytopes are always given in one of two ways: either the convex hull of a set of vertices, or the solution to a set of linear inequalities, intersection of half spaces. And these sets are given in neither. I mean, they are just collection of gradients of points along the orbit of some group action. Just a collection of points, neither convexity nor linearity, namely the fact that they are bounded by hyperplanes, is obvious. It's just not obvious. And nevertheless, there are convex polytopes, and the beautiful thing is now we have algorithms for this type of problems, right? We have algorithms to find, to solve scaling problems, also non-uniform scaling problems. In other words, we have algorithms to compute membership. What is a non-uniform scaling problem? It's membership in this in these convex polytopes. So say, aha, yeah, okay, what kind of polytopes that arise in this way are actually polytopes that might be interesting in a optimization setting. We suddenly have algorithms for them. So let me give you just some examples of such polytopes. I mean, they are very strange, some of them. So I have two parts. In the top, I have some sets of gradients, and it's not clear why they are polytopes. In the bottom, I have polytopes, and it's not clear what they have to do with groups. And let me mention some of them. So, for example, here's the first one, the Schur-Horn set. So I give you a symmetric matrix A, and consider, that's obviously a group definition, consider the diagonals of all matrices that are similar to A. Okay? So similar by conjugation. The set of vectors in R to the n, if it's an n by n symmetric matrix. And you can think about it. I mean, what kind of set is it? But the theorem above, it turns out to be a set of gradients. And by the theorem, it's a polytope. It's not obvious it's a polytope. This is not too hard to show, but it's a polytope. Something that's harder is the Horn polytopes. It's if you have three, let's say, Hermitian matrices, A, B, and C, such that A plus B is C, what can be the set of their, eigenvalues, vectors of eigenvalues? And these triples, they turn out also to be a convex polytope. There's a Braskamp-Libby inequalities that I didn't define, and maybe I won't. So anyway, there are polytopes that arise also there. That's examples of things that arise as polytopes, even though you don't see, I think, either convexity or linearity in the definition. On the other side, I already mentioned the Newton polytope of a polynomial, just a convex hull of the exponent vectors. It turns out to be to arise via a commutative group action on the polynomials, just by scaling multiplicatively the variables. And the Edmond polytopes also happens to be a moment polytope. They are all called moment polytopes. This is a matroid intersection polytope. This basically the convex hull of or indicator sets of bases simultaneously of two matroids, let's say M and M prime. Anyway, there are examples. Unfortunately, I have to say that all the examples I know, if you think from a combinatorial optimization point of view, while these give algorithms for them, it doesn't give new algorithms. Maybe of course the exception of the Braskamp-Lieb inequalities. Well, in fact, the top examples are new, only that they are not combinatorial optimizationally motivated. They are motivated from analysis or from algebra. I wish I found some open problem in optimization which is solved in this way. Okay, so I think okay, so I have some more material. I can let me ask Joel. I can explain a little bit more the connection to the skew fields and also to these Braskamp-Lieb inequalities. But maybe you think it's a good time to just ask questions and conclude this. It's up to you.
No, I think we could certainly take questions now, but that would be fascinating to hear more about this stuff.
Okay,
I mean,
so I'll tell you. So questions now. Any questions about this?
Can I just ask, are all the groups that you consider explicitly given as varieties, or are they somehow? Would you ever consider a group that was, say, a group that was the Zariski closure of something generated by a specific collection of matrices? Or?
Yes, it will work for any group, whether implicit or explicitly described. Only you want to be able, in order to run an algorithm, you need to be able to perform an action, right? You have to be able to multiply. I mean, the gradient descent step is multiplying by an element of the group, so you need access to this group somehow. I mean, the analysis would work, but in order to run an algorithm, you need access to the group. So there are very, if you just give me it as a variety, I would not know how to access the group. In terms of the analysis, again, as I mentioned, the constants controlling the number of iterations in these two very general algorithms depend on the representation theoretic data, the irreducible representations of the action. And again, if you want to compute them, you need to understand something about the group. And in such cases where it's just given as a variety, maybe you don't have access to this. We compute it in for various well-known groups, but they exist for any group action, but maybe inaccessible. Yeah. More questions?
Just perhaps a naive sort of open-ended question. So these moment polytopes are all polytopes. Indeed, it's very intriguing. Would something lead to? I mean, it seems to me that what I had expected would be something like semi-algebraic sets, perhaps, or would there be higher moments that would lead to things such as semi-algebraic sets? I mean, given that you're in a very algebraic context to begin with.
Yeah, I don't know. I mean, it's a good question, but I mean, I think that you get the best you could hope for. It's not semi-algebraic sets; it's a polytope. So.
No, I know, and it's also very, it's very intriguing.
Yeah, I agree with you. A priori, you can just expect a semi-algebraic set. I mean, just solutions to polynomial inequalities, but no, it's yeah.
I have a question. Is it obvious whether all polytopes arise as moments?
Yeah, but in a trivial way. It's a good question. In fact, all polytopes arise already, let's say, with integer vertices. they arise as moment polytopes because you can define them even of commutative actions, because you can take any polytope and make it a Newton polytope, namely make up a polynomial with these exponents, and it will be the Newton polytope of this simple commutative action by scaling. But that's not, it's sort of unfair. It's already an exponential description of something that would have been defined implicitly by a group action. So, but yeah, anyway, it is true. Every polytope is a moment polytope.
Thank you.
Okay, so let me tell you just maybe two more stories and then go to the end. So I mentioned, after showing you operator scaling, I mentioned some problems that it solves, and one of them we already discussed, so let me show you this. So first I want to talk about the non-commutative algebra and the skew fields very briefly. But I want to stress somehow, so this algorithm is proving identities, because in the next application we'll see that it's also proving inequalities. So yeah, I find it very mysterious. It's doing things in these two very different worlds. So starting with the work of Amitsur, who was the first to define free skew fields, and then with the work of Kohn, we talk about a set of non-commutative variables over a field. The field is normal, it's a commutative field. And we look at all non-commutative polynomials, so monomials have to care about the ordering of variables, but anyway, that's a very natural vector space, and this so far is understood, and now you want to close it and make it a field, and this is denoted something like that. And this is just, let's say, formally defined, take all rational expressions. Of course, you have to worry that you are never inverting a zero, and you have to worry about that fact that it's may not be very informative in the sense that there is no canonical description of an element in this field, but you can think of it, the field, as a field of including all of these expressions. And then, of course, it's closed because you can you allow all the operations of the field. And I want to stress that this is a weird field. It's not, the elements here are not of the form of a ratio of polynomials. Even this very similar expression, x inverse plus y inverse, you cannot write as a ratio of two non-commutative polynomials. You can play with it and check it yourself. I mentioned before, it's a very important theorem of Rethenau that this inability to simplify goes on and on forever. There are expressions that require arbitrarily high nesting of inversions. So it's, you cannot simplify expressions like this one. This is a very simple expression with two inversions. You cannot reduce it to having only one inversion. And there are of course, more complicated objects. And one, really cool identity that comes from projective geometry, actually, is this Y identity, which shows that, if this left-hand side has just two variables, not four as above, then you can simplify a nested inversion, just by exercising you play with the field elements, you multiply, you invert, you do what you are allowed, you add, you subtract, and you can make one expression equal the other, but it's not clear in general how you would do it. So it raises the question, when are two expressions the same? And that's that's basically the basic problem of any algebraic setting. When you have several representations of the same object, you want to know whether they are equivalent. So this is a word problem, testing whether a given rational expression equals another, or without loss of generality equals zero. That's a word problem. And I mentioned it's not obvious, it's decidable. And Kohn proved that he encoded this question. He encoded every rational expression. So he really had the analog, the completeness analog of Valiant's result in the commutative case. He showed that asking whether such an expression is identically zero is the same as asking whether a symbolic matrix over non-commutative variables is singular. They are identical. So there's always, you can always reduce to this linear matrix problem and ask whether it's invertible in this field. And this already gave it the decision algorithm, and what I mentioned, this one interpretation of our result is a polynomial time algorithm for this problem.
Could I just ask a question here?
Yeah.
So the question is whether a matrix over non-commuting variables is singular or not. So can this problem be formulated purely in terms of polynomials? Like, is there some kind of determinant?
Great question. Yes, yeah. There is a very elementary description of this, which is the following, but of course it requires a theorem that's proved by Kohn. So if we were thinking about a matrix in commutative variables, we may ask whether it's singular, or we may ask even about whether the rank is something like whether the rank of this n by n symbolic matrix is R. And we know what the answer is in the commutative case. The rank is at most R if you can write it as a product of narrow matrices, right? N by R and R by N. And in this description, the entries of these matrices will be rational functions in the variables. That's the commutative case. What Kohn proved is that in the case of non-commutative variables, you have much more rigidity, and exactly what you guessed is right. That if the rank is R, then you can write it as a product of such narrow matrices, and in fact, you can assume without loss of generality that the entries of this matrix are polynomials. You don't need rational functions. So in some sense, the definition is simpler. In fact, you can assume that the entries are just linear or affine functions. So again, the rank is R if there are n by R and R by n matrices whose product is the linear matrix we were given, and the entries are just affine forms, non-commutative. So this is one way to describe what the algorithm is doing, is actually computing this rank, in particular whether the rank is full, which is non-singularity, or not full, that's singularity. Yeah, thanks. That's a great question. More questions about this? Okay. So let me tell you a little bit, so I have 10 minutes or so, I'll tell you about Braskamp-Lieb inequalities, because they are really wonderful. It's a wonderful application, I think, of what we've done. Okay, so we are moving from algebra to analysis, and we are going to talk about proving inequalities now. So the set of inequalities that was introduced by Braskamp and Lieb, and it has this form. I'll talk about it soon, but basically they look like the integral of a product of functions is at most some constant times the product of some norms of these functions. So products of the integrals. So integral of products is most a product of integrals. This is something that you've seen a lot. I mean, there are lots and lots and lots of inequalities that look like that. And I list here some of them. They occur in analysis, geometry, probability, information theory, just lots of them. I'll give you a couple of examples that you will get familiar with it, and then I'll tell you the general result. Yeah, so it's I think it's a great insight that they had, that lots of things that were known fall into a very, very natural, simple framework. So let's talk about some examples that you've seen. So Cauchy-Schwarz inequality, here we have two functions from the reals. There are always, functions will always be to the non-negative reals. so maybe I should stress, we would like inequalities of this to hold for all functions, or all integrable functions, right? That's what an inequality is. It holds for every input. So what is the Cauchy-Schwarz inequality? You take any two functions like that, and when you integrate their product over the reals, then we know it's at most the product of the two norms, right? That's a well-known exercise. And you look at the norms used in this inequality, and you see that it's the L2 norms. And we all know and love this. And the question that one should always ask, at least in this context, is, can we put other norms there? And the answer here is well known. Helder told us you don't need the two norm. You can put any norms you want as long as the sum of the reciprocals is 1, right? So that's the Helder inequality. So it's another example of Braskamp-Lieb inequalities. And in general, we should be interested in the set of all possible tuples of norms we can put in such inequalities so that they will hold. And this is it. It turns out that you cannot put other norms. This condition is essential. And with this condition, you see that the constant in the inequality is 1, and it's optimal. You cannot improve any of these inequalities. Okay, so that's really an example where we understand everything. Here's another example where we understand everything. The Loomis-Whitney inequality. I just do it in 3 dimensions, and there are higher dimensional analogs. You've seen it as a volume inequality or entropy inequality. Basically, you think of a set in 3 dimensions. And suppose I give you the projections to each of the 2-dimensional spaces defined by the axis. And so it turns out that the volume is at most the product of these areas, square root. This is an extension of the obvious inequality that if you are in the plane and you project to the x and y coordinate, the area is at most the product of the length. Okay, so and it's not hard to prove. There's an entropy version of it. And what it says is now you have functions on 2 space on each of these. So the area is just a particular function we could have taken. Turns out we can take any 3 functions on 2 space. And the Loomis-Whitney inequality says that the integral of the product of these 3 functions over the 3 space is at most the product of the 2 norms of these functions. The square root is already implicit in the definition of the norm. Okay, so I don't know how many have seen this. It's very useful in analysis and also in combinatorics. And you can again ask whether, can we do what we did with the Cauchy-Schwarz? Can we replace the 2 norms with something else? And well, the answer is no. This is the only set of only tuple of norms, or 3 norms you can put, so that you will have any inequality with any constant. Here the constant is 1 again. So it's a different answer. Here you don't have the flexibility like with Helder inequality. Okay, it's another example. Let me give you one more example. It's this Young inequality. We are back to 2 space, but suppose I give you more projections than projections to the axis. I give you a projection to the x-axis, projection to the y-axis, and like x1, x2, and projection to their sum. So it's more information about the projection of this set in 3 directions, and ask you what is the best bound you can give me on the area of A, now that I gave you more information. And it turns out a special case of Young's inequality is this. I mean, you get, you look at the 3 half norms. And this is a general form for these 3 functions. Now they are 1-dimensional functions, these projections. The integral of this product over 2 space, but now we have 3 functions, is at most the product of the 3 half norms. And here the constant is not 1. It turns out to be something strange, like square root 3 over 2. But anyway, it's an inequality valid for all functions. And again, you can ask, can you do it in other norms? And I don't know what you would guess. Again, it's not the right form to ask such questions. But the answer is yes. I will not write the general one, but there's a set of norms that for which it works, and they also satisfy the reciprocal, satisfy some linear inequalities. And there's a really weird, bizarre constant that fits each and every one of them. So these are examples. And what Braskamp-Lieb again asks is, what about the general case? So what will be the data for a general case? We have a set of projections, matrices from n space to n sub j space. We saw examples. It can be anything, 1, 2, 3. We have m of them. And we also have a set of norms. And actually, you see the brackets on the left. It's really convenient to think of 1 over p as the norm. This turns out the right way to think about it. So a bunch of non-negative numbers, you can think of their inverses as the norms we care about. And this collection of these two tuples are what's called BL data, Braskamp-Lieb data. With this data, what you would ask is whether we have the inequality, that the integral of the product is upon the product of the norms times some absolute constancy. When is there such an inequality, and what is the optimal constant? You want this to hold for all tuples of functions, let's say integrable functions into non-negative reals. And we saw examples where such a thing holds and where we know the answer. So when is this so some things were known, beautiful things about this question. It turns out that the solution for feasibility is a linear program. It just, this is possible depending only on certain linear inequalities in these PJs. As in the examples we saw, this is true in general. So that's one result that was known. Another result is when it is feasible, Lieb characterized what is the optimal constant that can be achieved. It turns out that when it is feasible, what it proves that's highly, highly non-trivial is that the optimizing functions will be basically Gaussians with certain covariance matrices. But it's always Gaussians that make the constant worst. So in a sense, the optimal constant is given by some optimization problem over determinants. So you don't know what these covariance matrices are, but some of them work. And when you see, there's a ratio of covariances or ratio of determinants, and for us, having just worked out operator scaling, where the measure of progress was capacity, which is a ratio of determinants, this smelled like something that can be, can be similar. And indeed, we found a reduction from this general problem to operator scaling, which resulted in an algorithm that works in polynomial time. It, for any such data, determines feasibility. When it's feasible, determines the optimal constant, all in polynomial time, and it yields other structural results that were not known about the stability of this constant after perturbations of this, let's say, the projection maps. It was not known if you perturb some of the projections by a tiny bit, how it affects the constant or feasibility. And people use compactness arguments and so on. Our result gives also very good quantitative bounds on this type of question. Anyway, that's the story about Braskamp-Lieb inequalities. Let me I have some more, but let me conclude, because this is, so I want to tell you about this and about statistics, but maybe some other time. So just concluding, some things we've seen. So, we see how the, questions about algorithms and complexity, interact with lots of areas of math. One curious thing, I think, about the type of algorithms here, that the questions like operator scaling are patently algebraic, and nevertheless, the algorithm is, sort of dynamic or analytic. On the other hand, analyzing this continuous algorithm comes from algebraic tools, like tools from invariant theory and representation theory. Symmetry, maybe that's the most important thing to stress, that it appears sometimes it's not obvious that it's there, but you should look for it, and when you see it, it's very powerful. Some questions are many, but the algorithms in some cases are still exponential. I mentioned that having a polynomial time algorithm in terms of epsilon doesn't always solve the problem. In some cases it does. I told you I really hope to find more applications of this moment polytope optimization to combinatorial problems. Null problems in general, I mean, it's possible that they are always in P. We have many examples where they are, but some examples where are not, and I don't know. I mean, even the question of whether they are in NP intersect QNP is open, but at least this is known for some actions. And where does it get us in terms of the real problems we want to understand? I certainly do the commutative singularity problem and the relation to lower bounds, to P versus NP, and so on. You wonder whether this type of algorithms will be relevant for this. One thing I recently realized with Vissumakam is that at least this membership in this variety is not an alcon problem. There is no group action for which the variety of commutative singularity is an alcon. So it's sort of a barrier result. You prove that at least it will not come directly from this type of algorithms, because this algebraic variety is not an alcon. In general, which algebraic varieties are alcons is, I think, a very interesting question. I think that membership in algebraic varieties, the algorithmic question, is of course extremely interesting, and there are many, many more related questions. So let me leave you with, again, the reference to my book on complexity whenever you want to find out more. And thanks.
Thank you, Avi, for an absolutely fascinating tour of these areas. It's from my perspective, it's very rare that somebody will combine these algebraic and these analytic questions, right? Usually people tend to go firmly in one camp, and they don't speak to each other so much. And are able to make
there are many famous examples in mathematics where you do involve the analytic and algebraic, definitely in algebraic geometry, and Langlands programs and the Veil program, and there are in fact many of some great advances come from the mixing. This is another place where they mix extremely well, I think. Yeah.
Yeah, no, that's right. I mean, I think they're famous because they're not so easy, right? I mean, Langlands program is like this big this big thing. I mean, there is an anecdote by David Mador, this French mathematician. He says he was dining at the IHES at some point, and he was sat next to Israel Galfand, the famous mathematician, and he was asking him, well, what are you interested in algebra or analysis? And Mador said, well, I'm interested in algebra. And Galfand said, I don't understand why people are interested in algebra, because in algebra you write A equals B, but if A equals B, then A and B are the same thing. So really you're writing A equals A, and what's the point of that? And Mador's answer was, well, I'm not as smart as Galfand, so I wrote my thesis in algebraic geometry anyway. And people really tend to fall into two camps. Anyway, are there questions from the audience?
Dumb question. So you mentioned that cone. So the variance result that basically Sing is completely general for PIT. Commutative Sing is completely general for PIT. You said that, well, before that, Cone had proved the non-commutative analog of that.
Yes. So,
but are these results completely independent of each other?
No. Well, I mean, they were proven independently.
But one follows from the other.
But the Cohn's result, which was earlier, actually implies variance result. Okay. It works as well in the commutative setting, so it's more general. It was proven earlier in a different world. Yeah, it's only with hindsight that I realize this. But
so just a kind of more general question. You said at the beginning that if you can't solve a problem, you change it, and so let's consider non-commutative. But is there any way in which somehow this is somehow actually an important step in solving questions in the commutative world, or?
Yeah, so in this case, we don't know. So to your previous question, the completeness result of singularity works in both settings, and in fact, the non-commutative one implies a commutative one. But other questions, like determining commutative singularity or commutative non-singularity, here it seems that the commutative case is harder. Of course, we were hoping that the non-commutative singularity and the algorithms for it will advance us there. It seems that it didn't yet, but I should stress that there's another attempt of proving lower bounds, especially in the arithmetic setting, like lower bounds for permanent, separating it from determinant, which is the famous geometric complexity theory approach of Malmali and Sahoni, which raises lots of algorithmic questions in invariant theory. So towards the same goal, proving lower bounds. And it turns out that this work on operator scaling and this and the related things does help answer some of the questions and connects very well with the geometric complexity theory questions, even though there are two initially very different, seemingly very different attacks on the same problem on lower bounds. It turns out that they speak to each other more and more and very beautifully.
Thank you.
Other questions?
Yep, I'm curious whether there are intermediate cases between commutative and non-commutative, which have been studied. For example, I may decide that X2 and X3 commute when they sit next to each other, but otherwise nothing else commutes. So what happens there?
Yeah, it's a very good question, and I can say from what I know, it was not studied much. One can particularly look at concrete non-commutative algebras like algebra of quaternions or various matrices of algebras of matrices where you have non-commutativity, but it's sort of given to you explicitly. I don't know if anything was studied in the framework you suggest, where you have some relations, right? So in a commutative setting, we have all relations, xi, xj minus xj, xi is 0. In the non-commutative setting, we don't have any of them, and you're asking maybe about introducing some relations. So I don't know. I mean, it's a very good question to understand what is, where does it break? Well, and I cannot answer this.
Thank you.
So just along the lines of the previous question, so you mentioned algebras of matrices. So so these are kind of obviously they're not free because they satisfy polynomial identities, but then you have some control over the polynomial identities that they satisfy because you have this Amitsa-Levitsky theorem.
Right.
And I've seen this used for doing polynomial identity testing in non-commutative setting.
Yes, so this is, you can think of the operator scaling result as a sort of vast generalization of this. In the works that you mentioned, I can give you two non-commutative, or let's say one non-commutative polynomial, maybe by a circuit, and you wonder whether it's identically 0. You can ask, what's the algorithmic complexity of this? The Amitsa-Levitsky theorem, which basically gives sort of a dimension bound on the size of matrices you need to plug in. So it's a non-commutative expression, but you can plug matrices into it. So it tells you that you can plug in small dimensional matrices and check this identity, and this will give you an algorithm analog to the probabilistic algorithm I described in the commutative setting. You don't plug numbers, you plug matrices. So you can get a probabilistic polynomial time algorithm for this non-commutative identity testing. It turns out that if the polynomial is given by a formula or by a branching program, Ran Raz and Amir Shpilka actually have a deterministic identity test. But this works only when you have polynomials, namely only addition and multiplication. The consequence of the operator scaling result says that even if you allow inversion, so now you are now in the field rather than in the algebra, you still get a polynomial time algorithm for such equivalences. So it's true. It is, and I should say, this is very related to your comment about Amitzur-Levitsky, the Amitzur-Levitsky theorem. Indirectly, what the bounds on the invariant polynomials give is an upper bound on the size of matrices you can plug into these identities. And so that, if they satisfy it up to that size, then they are satisfied always. This is sort of more or less the meaning of the degree bounds there. This is a consequence of a characterization of, a generating set for the invariant polynomials of this action. And so it's highly non-trivial. And here I should mention that the Derksen bound, the exponential bound on degree, which is an exponential bound of size of matrices, is no good at all for this type of algorithm, because you cannot afford to plug exponentially large matrices. So as I showed you, our analysis is indirect. It's using the degree bound in the analysis in a very different way. But for this left-right action, Visum, Markham, and Harm Derksen proved that there is actually a polynomial bound. So they prove a big strengthening of the Amitzur-Levitsky theorem for rational expressions, allowing inversion. So there's a beautiful strengthening of this theorem to allowing inversions.
Yeah, I mean, I guess the nice thing about these rings generated by matrices is, well, they do satisfy polynomial identities, but because they do, you can actually form the ring of quotients in these PI rings, so you can form this ring of quotients in a nice way.
Yeah.
Well, they're all domains. So yeah.
But it's really amazing to what extent these very questions were studied in very different parts of algebra. In areas that don't talk to each other. It's really, the non-commutative algebra is one field, and invariant theory, which of course is commutative, is another, and many things proved in one are useful in the other, and we utilize some of that, but it's they each developed through their own logic and their own goals, and derive things that having more contact with them would have been good for both. It's really interesting.
Other questions or comments for Avi? Okay. Well, I think it's over here in Europe, it's 6 p.m. on the Friday afternoon, so maybe people are, this is a very fitting way to end the working week. Thank you so much, Avi. That was absolutely wonderful. Wonderful tour. So I think Philip wanted to say a few things about the next talk.
I just wanted to, well, of course, thank Avi again, and thank you, Joel. I think you did a very good job. And yeah, in 2 months, we will have another talk by James, also known as Ben. That's all I have to say. Thank you.
All right. So thanks again, and have a good weekend, everyone.
Bye-bye.
Thank you. Bye.
Bye.
Right.
Thanks and bye.